I guess I'd like to start off by having a little celebration and an acknowledgement and a demonstration all in one. It's far too early to be drinking wine. I'm just using this as a mechanical sort of stable platform for my demonstration. And this is my, if you like, flaccid through to slightly more erectile acknowledgements for the KTN group and indeed for the European Space Agency. The reason for these acknowledgements will become apparent in just a moment in the presentation. I hope I don't set all the alarms off, although I believe that's a smoke rather than an ion detector, but let's try and see what happens. So let me raise the flags to both the KTN, I don't know whether you can see this from the back, and indeed to ESA. So an acknowledgement, or a pre-acknowledgement, both to both organisations that I have been and indeed continue to be involved with. What I'd like to present is, I guess it's in the form of a sort of potpourri, a case study of my activities. As was already mentioned, I came into the multidiscipline interfaces, mechanical engineering, materials, and latterly biology. This comprises biomedical engineering, incidentally, through space ventures. The thing I'd like to talk about is the origins with ESA and with ESTEC and continued involvement, microgravity, life sciences, research in space, what I call converting technology, if you like, the technology transfer, the smart materials technology, a bit of an overview, and ultimately technology transfer, medical uptake, and consequent commercial activities. I started off on the planning, or possibly even the pre-planning days of Eureka. Eureka being a common user scientific payload satellite which goes out into slightly cleaner low gravity. By that I mean, 60 kilometers off the surface of the Earth, you're 10 to the minus 4, 10 to the minus 5, possibly G. It's a bit noisy in terms of gravity perturbations. And if you want to find out about life sciences, what happens to a plant, for example, in the low gravity environment, the bottom line here possibly being, as was already mentioned, if you go to Mars, it's actually difficult, if it's a manned flight, bringing enough sandwiches for your return trip. So developing methods to produce the food, if you like, for the astronauts or payload specialists or other forms of specialists is problematic. So what happens to a plant if you put it into a low gravity environment is of interest, and to conduct appropriate research in that area, you need clean gravity. So Eureka goes about 1,000, possibly more kilometers away from the Earth, and the gravity perturbations are a little bit less. So this is essentially the vehicle here. And a feasibility was initiated by ESA, ESTEC, to develop this automated testbed facility. My particular thing was life sciences and how to design the selection of materials for these sort of scientific experiments. It's not a trivial pursuit, I hasten to add. This is in conjunction with Dornier and latterly with several other aerospace companies and indeed my university, Brunel University, the Institute for Bioengineering. This is the model we eventually developed, and I'm racing on something like 10 years here to develop this. This is a fully automated testbed facility. It's definitely not flight hardware. We discovered about 2 years into the venture doing these designs that we don't actually have the technology. Arguably we have the materials, but we don't have the overall technology to cross these disciplines and to harden up an essential prototype into flight hardware. The biological to materials interface, man-made materials interface, is a difficult area. What this consists of are several different stages, 37-degree incubation stage, if you like, for cells, things of that type, a freezing stage, 4-degree, microorganism storage facility, micro-G centrifuges, insect handling, experiment container, pick-and-place devices. And there lies the essence. Pick-and-place devices to handle these living organisms. This, as you will, I'm sure, understand, this is an automated facility. There's no one around to make corrections if something goes wrong. So a robot which takes your plant sample container, your insect container, from one position to another position, simple pick-and-place device, doesn't actually require much intelligence to do that. If it's a simple pick-and-place device, it needs a low IQ. And in developing this, we had some fantastic technology, complex servo and stepper motors and feedback systems and so on and so forth to handle these robots. And I decided to throw all these things away and simplify it by using simple actuators, and this is where the shape memory alloy materials come in. We needed to do successive generations of these living organisms to find out what changes may have occurred at the metabolic, the cellular and other structural properties of living organisms. So 6 successive generations from you go off to Woolworths and buy some seeds and you put them in your flower pot, the vehicle takes off, is in low gravity conditions, the plant then grows in its flower pot, you take the seeds from that from that mature plant, plant them in a separate container and so on and so forth, so 6 successive generations, and the multiplication factor then will determine changes that may have occurred because you're in the low gravity environment with, incidentally, a different radiation profile as well, which is something we have to take into account. So going back to my actuator, get rid of these micro-step motor servo control system, feedback systems, replace it with an actuator schematically shown there, a shape memory alloy spring. If you remember my flag here, the reason that worked is because down here there's a small piece of shape memory alloy which has a memory like that. However, when it's cold, I can simply deform it, bend it. Nothing actually happens, and just to show I wasn't actually cheating, I can actually do it again. So sorry, it's deformed in the cork. However, that's how it works. When it's cold, it's actually very deformable. When it's warm, the memory comes back. That's one of the generic forms of this particular material. So if you put a spring in a cylinder, as I've shown there, and you resistively heat it, it gets warm, the spring expands, you've got a simple actuator. There's the basis of a pick-and-place device. If you liken that to my arm, for example, going out to reach, all I'm doing is a series of simple actions, and they can all be done using this technology. Now, this was adopted on the biosample module, as it was called, by ESA, and it was successfully demonstrated, and there's a whole range of other things here, clutch mechanisms and other mechanical mechanisms, which we converted to shape memory alloy. Okay. Let me just talk about this technology, expand a little bit, but rather in an overview mode. There are approximately 15 forms of these shape memory materials existing, consisting of these essential elements or various combinations of these elements. The reason you get this movement, this change, is simply, I guess the simplest way to describe it is a change of the crystalline structure of the material. It changes from one to another form on the application of energy, in this case heat, thermal energy into it. The classic body-centered cubic lattice, face-centered cubic lattice to an orthorhombic form. So essentially you've got a cube which then moves, sorry, the other way around, you've got an orthorhombic, a rhomboid form which changes into a cubic form, and the small movement at each crystal amortizes itself into a gross movement of the alloy itself. Okay. Thermally induced shape recovery is one of the properties. The other, what I call generic property, is simply a very extended elastic range where you can deform the material, so super-elastic as it's called, or pseudo-elastic. What that means, if you compare, let's say, with a spring-tempered carbon steel, you can induce